everyone. I am Syam at Naga, Golla, and today I will be presenting my project on the evolution and application of generative AI, particularly focusing on recurrent neural network and long short-term memory networks. Over the next 30 minutes, we will explore how these neural networks have revolutionized generative AI, particularly in natural language processing, music, and art creation. In this generative AI has advanced remarkably thanks to RNNs and LSTMs like recurrent neural networks and long short-term memory networks. Their ability to handle sequential data has had to breakthroughs in creating um, coherent text, music, and art mimicking human sensitivity. Our journey through the project has encompassed a detailed analysis of how these technologies process and generate sequential data, offering insights into their capabilities and the challenges they've overcome, whether it's text, music, or even power consumption data. RNNs and LSTMs are reshaping how we think about data analysis and creative generation. Just a second. And here you can see the part one, an essay on journey of generative AI from Boltzmann distribution and Markov chain to language model. I have attended the seminar and understood the significant importance of RNN in the evolution of generative AI. Uh, Generative AI started with the basic models, but now evolved to sophisticated systems like RNNs, which are designed to handle sequential information such as text or music. As I said before, this capability is crucial for tasks where context from previous data points is essential for accurate prediction. RNNs, for instance, can retain previous information, helping generative coherent sequences based on learned patterns. For further advancements, led to the development of LSTM network, a special kind of RNN capable of like recurrent neural network capable of learning long-term dependencies. Traditional RNNs, like recurrent neural networks, often struggle with the vanishing gradient problem, where they lose track of earlier data in long sequences. LSTM solve this by introducing like long short-term memory networks solve this by introducing gates that regulate the flow of information, allowing them to remember or forget data, which is crucial for tasks involving longer contexts. Um, where recurrent neural networks are a part of neural network structure, which is designed to handle the time series data such as text, image, and video, as is mentioned. The architecture of the recurrent neural network is different from other types of neural networks too. A group of interrelated nodes is present, with each node responsible for processing an element in the sequence. These nodes are organized in a chain like structure that allows information to flow from one node to the next. Like hidden states are an important feature of recurrent neural networks because they retrieve information from previous nodes in the chain and use it to influence the processing of future elements in the sequence. Like you see in the structure below, one over here. On the primary challenges in modeling sequential data is capturing long-term dependencies. The issue with the traditional RNNs is complicated by the vanishing gradient problem, which suggests that as time passes, gradient decreases. The problem is overcome by closed loop discontinuity in long short-term neural network, long short-term memory networks, which enable the network to learn, to remember, or forget information. This allows for the capture of long-term dependencies in long short-term memory networks, which results in chains that are more coherent and structured. In RNN and LSTM, networks are widely used for generation of text. LSTM-based language models have been very successful in producing human-like text. The models can learn about the structure and semantics of language by using large text corpora to create sentences, paragraphs, and articles that are both contextually sound and meaningful. It involves the development of content, chatbots, and machine translation. Uh, like the success of LSTM networks has also led to advances in generative model training techniques. Techniques such as teacher forcing and planet sampling have been developed to stabilize training and improve the quality of generated sequences. These techniques have helped overcome some of the challenges in sorry in training recurrent neural networks and contributed to the overall success of generative AI. Finally, in the conclusion of this essay, recurrent neural networks and their variants, especially long short-term memory networks, have contributed significantly to emergence and advancement of generative AI. Through these advancements, AI has expanded its capabilities to include artistic expression and creative techniques such as copywriting and music composition. The advancement of research in this area will result in further developments that will shape the future of AI generated content. When we are moving to the part 2, here we have a dataset overview that we have downloaded from online to um, for our forward process for project. Here I have downloaded, I taken the dataset, a name of household electricity power consumption. Here, as you can see, the like link to the source to download the household electricity power consumption dataset. Moving to the description, the measurements of household electricity energy consumption at a 1 minute sampling frequency over a period of nearly 4 years. Various electrical quantities and secondary measurement values are available. This dataset consists of 2 million more than like 2 million data points, which is collected from the houses located in Squax, which is 7 kilometers of Paris, France. This data is collected between December 2006 and November 2010. The dataset includes the attributes from date, time, um, global active power, global reactive power, voltage, global intensity, submetering 1, 2, and 3. Moving to the data dictionary, as you can see, the date is collected for recording data frame, and the time is for the time according to the process going on, and the global active power has averaged active power in kilowatt, minute averaged active power in kilowatt. For global reactive power is household global minute average reactive power in kilowatt too. The voltage is minute average voltage in volts, and the submetering one, it corresponds to the kitchen containing mainly a dishwasher, an oven, and a microwave. And the submetering two is corresponds to the laundry room containing a washing machine, a tumble dryer, and a refrigerator and a light. And coming to the submetering 3, it corresponds to an electric water heater and an air conditioner. Um, this is the overview of the data set we have downloaded from online. And moving to the part 3, it is a simple RNN with sine wave data. Um, Now, next, let's look at our experimentation with the simple RNN model. We applied a simple RNN to model sine wave data, aiming to capture the periodically typical in time series data. This architecture of our RNN included layers to recognize patterns over time, which is essential for tasks like speech recognitions. To train the model, we split 2048 data points into a training data set and testing set. We used the max minimum min max scalar function to normalize the data and build the model with a simple RNN layer. To train the model, we split 2048 data points into a training set and a testing set. We used the min max scalar, as I mentioned below earlier, function to normalize the data and build it in model with a simple RNN layer containing 18 neurons and a dense layer. The model was trained with the mean squared error, loss function, and Adam optimizer. Upon evaluation, you can see we imported some libraries and to generate the sine wave data, as you see in the screen. In this project, we working on 2048 data points from 0 to 84, as I mentioned below. Here is a code to generate sine data. Here is the code to build simple RNN model. Like I used both layers simple RNN with 80 neurons and a fully gated neural network. Now set the string length to 50 to predict the 51st value in the data set. Set this to 1 because we only have one feature in the data set, like the sign. Then compile the building model using the mean squared error, loss function, and Adam optimizer, as I mentioned below. Here's a code for to build simple RNN model. Let's moving on to the upon the evolution. After training and testing the model, we saw that the model's loss decreases significantly over time, indicating effective training. The predicted sine wave values closely follow the actual wave and the line graph, demonstrating the model's ability to handle sequential data. After conversation, the properties will return to their original values, added a new column for predicted values by a name predict. Below is a screenshot of the dataset updated with the actual and predicted values. Now we see the predictions on the data. With the training dataset, however, the small gap between these lines may be due to loss value and loss value as discussed above. Uh, Let me show you the coding file as I have here. If on a simple to build, train and test a simple RNN on sine wave data. Here, as you say, as I mentioned, the libraries that what I imported here, and the code for to generate sine data. You can see the values over here. You can see the graph that matter graph that obtained as an output. After loading the data, you can see the sine values over here, 2048 data points. You can see the codes over here, and I mentioned the predictions too. After building the data, compile model, transfit model, you can see the line graph over here, and finally the predictions as it mentioned below. As I mentioned earlier, you can see the line, the graph that appear finally as a for the sign and prediction over here. The blue line indicates sign and the orange wave indicates predictions. This is all about simple RNN with sine wave data, and I have used coding file. Moving back to the part 4, here uh, simple recurrent neural networks like a long and a long short-term neural networks. Here I'm explaining the vanishing gradient problem. The use of activation codes that reduce the loss function to zero in neural network architecture is causing difficulties in training the network, which has become more complex over time. Reason in the sigmoid function, the activation function reduces a large input space to a small input space in the range 0 to 1. This causes a large change in the input of activation function to lead to small changes in the output. So the distance becomes small. As you can see over here, the distance become small uh, from figure from the figure over here. We observe that as the sigmoid input values increases, its derivative output decreases. For shallow networks with fewer layers, this is not an issue for this activation function, but as the classes increases, the gradient becomes too small for the training to work effectively using back propagation. We can find the gradient of the neural network. This helps to find the chain rule. This helps to find the back propagation of network by transferring last year's derivative to the original layer. Using the chain rule, the derivative of each layer is multiplied across the network, to calculate derivative of the original layers. For example, if n layers are used, then the activation function used by those layers will multiply those n numbers, causing the gradient to decrease exponentially as we progress towards the initial layer. The simplest solution is to use functions like ReLU, which do not drift as a layer process. Another solution is batch normalization. The problem arises when a large input space is mapped to a small input space, causing the derivative to disappear. This reduces the problem by normalizing the input so that the determinant of the input does not exceed the outer edge of the sigmoid function. As you can see in the next exporting gradient problem, the direction and magnitude of the error gradient are determined during training of the neural network and are used to update the network's weights in the appropriate direction and and to the appropriate degree. Um, as a result, large updates of neural network weights will lead to network instability. NaN values can appear when weight values reach an extreme point that causes them to overflow. Uh, Gradient explosion is a recurrent neural network can at worst result in an unstable network that cannot learn on long input data sequences, and an unstable network that cannot learn from training data. And the solution for explosive gradients can be handled in the various ways. Some best practices are listed in this section. In this section over here, um, exploration gradient is a deep neural networks can be avoided by reorganizing the network layers. And the second one is due to inherent instability in training recurrent neural networks. The brag exam gradient exploding phenomenon can occur in recurrent neural networks. Long short-term memory networks units and potentially related gate-like neural network structures can be used to attenuate the burst gradient. A newly recommended method for recurrent neural networks used in sequence prediction is to apply long short-term memory units. Even with the very deep layer perception networks and a large batch sizes, as well as LSTMs with very long input sequence lengths, exploding gradient can still occur. If gradient explosions still occur, you can test them and set a gradient size limit which while your network is training, we call the gradient clipping. The limitations of this ripple neural network are feed forward neural networks and the multi-layer receptors are different names for simple neural networks. They are made up of weighted conceptions. They are made up of weight consumptions um, between layers of neurons. The data is received by the input layer, processed by the hidden layer, and the output layers gives the desired uh, adjustment strategies such as dropping out, losing weight, and stopping early can help minimize overfitting. And we then built the LSTM model with three layers, each followed by a dropout layer to prevent overfitting. The model was compiled with the Adam optimizer and trained over 100 epochs, showing strong performance in both the training and testing datasets. To test the model forecasting ability, we extend the dataset with new data from July 2021 to November 2021, retraining the model. Sorry. Um, Thanks to these gates, LSTM has a revolutionary generation music competition and image synthesis, producing high quality outputs that closely mimic human creativity. And the advantages of LSTM are long short-term memory is a unique class of RNNs capable of learning long-term dependencies. After the introduction of Creator and Screamer in 1997, many people improved and popularized them. This repetitive module is a typical RNN which have a very basic structure like a single tan layer. As you see here, all three gates are present in LSTM to save the and adjust the cell state. The next step is to select new data to store in this cell state. Moving on to the part 5, RNN LSTM with time series data. Here we build with the same libraries as we take earlier. Here we build an LSTM neural network, like historical stock price data is loaded from the provided CSV file, like the cell CSV file. I'm providing it over there in the description. Explore the structure size, explore the structure, size, and data types of the data set. Perform statistical aggregation to understand the distribution of data. The total length of the data set is 1381 and the columns are 7. We have specified a total length of 60 as an input string. uh, Filter the dataset to only include closing prices. Observe closing prices over time for complete details. Divide the data into training set and test set. Reserve 10% of the data for testing. After splitting the dataset for training and testing, the total test length is 138 and the total train length is 1243. Here you can see the set percentage of data for testing. Uh, Here you can see the output too. After these we need to train the model, scale the training and testing data testing data using min max scaler to normalize the values between 0 and 1. The dropout layer is set to 20% and the layer is dense as you see it in the build LSTM model. Here you can see the compile model output too. After compiling the model, up, uh, after these we need to test. Design a sequential LSTM model with 3 layers each followed by a dropout layer to prevent overfitting. Compile the model using the Adam optimizer and the mean squared error loss. You can see the line graph over here as an output that train the model for 100 epochs using time series generator, extend analytics to predict future stock prices beyond the original data, created a new time series generator for forecasting, train the model on the extended dataset by 100 epochs. After these retraining, the screenshot below here shows a comparison between test data and expected output. We see Tesla stock forecast has dropped from the result. It can be concluded that buying Tesla shares will be risky, become the expected value drops simplify as you see in the graph over here. The forecast, the model has now been retrained again using the new data set from July 2021 to November 2021. The chart below shows the plot to validate the model performance on the dataset most recently. The model shows accurate results in predicting both the test and predicting future stock prices, as you can see in the pressure. And I mentioned overall the percentage of data for testing, how many layers, number of neurons, any dropout layers, with dropout layer, percentage, length of the time series, the input sequence, batch size, number of epochs of training that I have used. I mentioned everything over here. Uh, and you can see the coding file too in here. LSTM with time series data. Here you can see the libraries after loading the data and import, giving the inputs, plot fig configuration. You can see the length and you can see the output length for percentage of data used for testing. You can see the output over here. This is the training and fitting prediction. 100 epoch, you can see the graph over here and 100 epochs over here. See, out of 100 epoch over here, the output for this Tesla sales forecasting. Yeah, I'll keep this IPMD file in the description too. Let's moving on to the part 6, redesign the LSTM neural network to improve performance. We to improve the model performance, we redesigned the LSTM neural network. We adjusted the architecture, increasing the neuron count in each layer to 60 and changing the training or test split ratio. We also modified the batch size to 40 and extended the input sequence length to 61. You can see in the figure. This redesigned model showed improved performance in terms of loss metrics and loss and learning capabilities. A comparison between the two models revealed that while the loss histogram and redesigned model is continuously zero, the prediction of graph were similar, indicating comparable performance. And you also see the percentage of data for testing how many layers. I mentioned everything mentioned below LSTM here too. Number of epochs used, batch size, length of time series data in sequence, if dropout layer, percentage, any drop of layer. I have mentioned everything over here. Moving on to the coding file. See, just a second. Is moving on to the coding file. Current neural network, support, line graph, everything over here, 100 epochs and line graphs, everything here. Comparing the two models, we find that the loss performance of the model is improved in section 5. The loss histogram of the redesigned model is always zero, indicating that the model has no error. When comparing the prediction graphs of the two models, we found that there is not much performance in the model predictions. The predicted values for the models are the same, even if the number of neurons in the two models is different. As you can see below here, the simple RNN and LSTM models. Um, moving on to the the comparison. Moving on to the part 8 project report. Uh, here Here, after all these introduction of about everything regarding simple RNN and LSTM models, what I understand is because understanding these both, because they are the only type of neural networks with internal memory. RNN are powerful. RNNs are powerful. Recurrent neural networks are relatively old algorithms, as are other deep learning algorithms, although they are first developed in 1980s. Uh, so comparing 1980s, their full potential has only computing power. The huge volumes of data are now worked with, and the development of long short-term memory networks in 1990s. RNN can predict events with a high accuracy thanks to the internal memory, helping them remember important details about the information they receive. Uh, for sequential data like time series, voice, text, financial data, audio, video, weather, and many more. Compared to other algorithms, recurrent neural networks can provide a much deeper understanding of a sequence and its effect. Therefore, it is ideal for learning from important events that have very long time intervals between them. LSTM is capable of reading, writing, and erasing data from its memory. This memory can be considered a closed cell. A closed box is a box that selects the which information to store and delete based on the weight it places on each piece of information. Weights are used to assign importance, and the algorithm also learns them. Essentially, this indicates that it gradually discovers which information is meaningful and which is not. Therefore, there are three ports in the long short-term memory cell center: forget and exit. Um, like long short-term memory cell, enter, forget, and exit. These gates control whether data is discarded as necessary, allowed to assign output to the current step, or allowed to input data. In conclusion, our project demonstrates the capabilities of RNN and LSTMs in handling complex sequential data. The evolution of these models has led to advance in generative AI, opening doors to new application from automated writing to music composition and financial forecasting. Future research could explore further refinements to LSTM architecture and delve into new applications for those models, expanding the scope of generative AI. Uh, Expanding the scope of generative AI. Thank you for your attention, and I welcome any questions you might have as a comment. You can see all the other files that I have used in this project and that have Then I created this project with all the Jupyter links, Jupyter notebook links, and CSV files. I'll mention it in the description too. Thank you very much.